So let's look at multiplying a normal number with a subnormal number and getting a subnormal result. So if you go to the resources section, open up the spreadsheet and make sure you're in the tools tab here and click on floating point multiplier. Now we're going to multiply the largest subnormal number. Now the largest subnormal number is in this little text file, so I've left the text file there as well in the resources section. Copy that and paste it in. Now this is the largest subnormal number, so if we were to multiply this by a fractional normal number, we're going to get an even smaller number. So let's say we multiply it by 0.1. Now you can see we're going to have a normal times a subnormal, giving a subnormal result. So the question then is, how do we create the exponent of all zeros? Because we know it's all zeros because it's subnormal. And how do we create the mantissa? Well, we can't create the exponent using this usual route. We won't get any valid answer. All we need to do in this case here is we just force the exponent to all zeros. So we just make all 8 values of the exponent 0, and that's all we have to do. So all we're really interested in this section here is how to manipulate the mantissa to get the right value. So let's have a look and we'll see what the right value is. So you can see that after the multiplications, this is our 48-bit multiplication, these are our 2 leading bits, and our decimal point is at this point here. So we're going to have this 11001100, and it will continue along. And you can see that the correct answer is in fact going to be 3 leading zeros, and then it's going to be 1100. So we can see then that if the decimal point was originally at this point here, then where would that decimal point have to move to in order to get what we have below? Well, the decimal point is going to be after the first 2 ones. So that's the first 2 ones there. So the decimal point originally sits in that position. But for the correct answer, the decimal point is going to have to move 1, 2, 3, 4, 5 places. So now the only thing we're interested here in this scenario is how do we generate that number 5? So let's have a wee look and we'll see how we're going to do that. And it's no surprise we're going to use the exponent values for x and for y. So we go through the same process we've seen in the previous video. We've got our biased exponent for y, which is all zeros. In that case, we would have a value of -126 for the exponent. But then what we said is we're going to count the leading zeros and we'll subtract off the number of leading zeros. So in this instance here, for the number here, the subnormal number, that's the y, you can see that there aren't actually any leading zeros. But remember, we have to include the hidden bit. So this is the 24th bit, and for a subnormal number the hidden bit is going to be a value of 0, so we have to include that one. So that means we're going to have that value of 1 for the leading zero count. So we subtract the 1 for the 126, we get the -127. So for the x value, which is a normal value, we just go through the normal process. We have a value of 123. We subtract off our bias with -127. We got our unbiased value. And then we add the 2 unbiased values together. We get a value of -131. And then finally, we add on the value of 127 to get again the biased value. So we get a value here of -4, but that's not quite right. We're out by 1. But what we can do is we can just subtract 1 off of that. So if we subtract the 1 off of it, we get -5. Now, of course, in this instance here, we're going to have the value of a negative as opposed to a positive value, but that doesn't really matter. All we're really bothered about is ensuring we get the absolute value of 5. And that's what we've got in this case. We've got an absolute value of 5. So let's put in another value just to, well, I'll put a couple of values. This will go 0.001. In that instance then for 0.001 you can see above that we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. So we'll have the 9 zeros, but you can see that it's going to start from this position here. This is the decimal point, so it's going to have to go another 2 places. So it's going to go those 2 places, that's 2 plus the 9, which is going to be 11 places, and you can see we've got the value of 11. So you can continue and you can test out this with several other values. So let's say we go to, well, one thing to note, if we go 0.01, and if we look at this value here, which is our xe plus our ye, so these are the unbiased exponents, and you can see it's a value less than minus 126, and as I make this smaller and smaller, then it's minus 137, minus 141. Now that's going to tend towards minus 149. So eventually, if you pick the right number here, that will tend towards minus 149, which is going to be the smallest subnormal number. And anything lower than that, it's going to tend towards an underflow towards 0. But if we were to go the other way, let's say we had a value of 0.9, you can see this value here gets to minus 128. Okay, now if I head up along here, it will never actually get down to the 127. Or in effect, if you look at this number here, it will never get to the value of 0. And it only goes to the value of 0 when eventually this 0.999 actually gets rounded up to a value of 1. Now in this instance here, I've taken the value of 1 and I've actually processed the value of 1 in the same way we would process plus and minus infinity or not a number. I've done it separately, so it doesn't run through it won't run through any of the design. It'll be done separate at the beginning and we'll get the answer at the end. Okay, so that's really covering the normal times the subnormal, giving a subnormal result. So there's just one other thing that we should test here, and that is that when we looked at the last example, the normal number was a fractional number. But in this case here, we've got normal times subnormal giving a subnormal result, but the normal number is no longer fractional, it's a whole number. And it's worthwhile to check that these work as well. So you can see in this instance here I've got 1e to minus 40 times 50, and we got the result up here. So let's check and see whether the values work for this as well. So in this case here, the output here is going to be 0, 1, 1, 0, and you can see up here we've got our 0, 1, 1, 0. Now the question then here is, how many decimal places must this move in order to get this result here? So if that's where the decimal place originally is, so it's between the first, after the first 0, 1, so in effect it's at this point here. So it's going to have to move 2 places, so it's going to have to go 1, 2 places. And you can see here that when we work through the same result, we get our value of 2 here as well. So it does all work. Now that we've understood, or we see how this is going to work, let's go and we'll write it down in a bit more detail so that we really understand it and the algorithm is obvious to us. So in order to multiply the normal number with a subnormal number and get a subnormal result, the first thing we have to do is ensure that the unbiased exponent values, either ex or ey, depending on which one is the subnormal number, is going to be given by the value minus 126 minus the pre-leading 0 count. So this is the number of leading zeros in the original subnormal number. And remember to always as well to add in the hidden bit, which is the 24th bit, which is also a 0. Now in order to work out the exponent value, we just force the exponent to be all zeros, so we're just going to be left with 8 zeros, so that's straightforward. And in the mantissa, it's going to shift the decimal point to the left, and it's going to shift the decimal point to the left by a value of our EX plus our EY, so our unbiased exponents for X and unbiased exponents for Y. And remember, one of these has been changed because it's now this value here, plus the bias, which is 127, and then we add on the value of 1. Now I've got the modulus around this because we're actually looking for the absolute value of this. But that's going to give us the correct number of decimal places that we have to shift the mantissa. And remember, whenever we've shifted mantissa, we're going to have to add in the missing or leading zeros. So that's all there is for this video. We'll go on to the final scenario next, where we multiply the normal with a normal and get a subnormal result. So thank you for listening. I'll get you on the next video. Goodbye.